So we have the double integral over r of y squared dA, where r is the region bounded by the ellipse 4x squared plus 9y squared equals 36, x equals 3u, and y equals 2v. So, you know, if you like steps, I would first find the transformation. It's given to you. It's given to you, but let's identify it. T is going to be equal to, and it really is T of uv, is going to be equal to basically the transformation equations after the semicolon. So x equals 3u and y equals 2v. And then in the same first step, you want to use T and go ahead and find the Jacobian right away, right? So let's go over here a little bit. The Jacobian of x and y with respect to u and v. The way to remember the order is the inputs, which are u and v, when you're given t, or you can find t, the inputs are u and v. When you're given t inverse, the inputs are x and y. And the inputs are always on the bottom. The Jacobian of x and y with respect to u and v. So, by the way, I want to show you something neat here. You don't actually need to find the Jacobian here. The reason will become apparent, but let's go ahead and find the Jacobian, and then I'll show you another way to do this one. So the Jacobian, remember, then you would look at your first equation and say, take the derivative with respect to u. What's the derivative of x with respect to u? 3. Look at the second equation, take the derivative with respect of y with respect to u. 0, right? And then look at your first equation, take the derivative with respect to v for this row, this first entry in this second row. That would be 0, right? And then look at your second equation, take the derivative with respect of y with respect to v. 2, right? And then these are determinant bars, so you just, what do you get when you take the determinant? Just 6. And so that's the extra factor you're going to plug in your integrand. So what's the other way? Well, when x is in terms of just u and y is in terms of just v, you can take the differentials the way you're used to. Look at what happens. What would dx be? 3 du, right? And what would dy be? 2 dv. And if you fill these guys in place of your dx and dy differentials, you're going to get a 3 times 2, which is 6, right? So in this particular case, the Jacobian, you don't need it. It's only when x is a mixture, when you have x equals a mixture of a formula involving u and v, and y equals a mixture of u and v, that the Jacobian becomes necessary. Just an interesting side note there. Okay, let's go ahead and find our region S. So, couldn't we just directly, since we have a single boundary equation, couldn't we directly plug in x? And couldn't we just directly plug in y, x in terms of u and y in terms of v? Yeah. And notice, I guess I said it in the problem, that's an ellipse, right? 4x squared plus 9y squared equals 36 is an ellipse. And we would like to turn an ellipse is really just an elongated circle, right? A stretched out circle. And so it shouldn't be too hard to turn it back into a true circle. And that's what we're doing here by this substitution. So let's do it. Okay, so if we plug in 4x squared, if we plug in 3u for x, we get 4 times 3u squared, right? Plus 9 times 2v squared equals 36. Do you guys see what's going to happen now? By the appropriate choice for x in terms of u and y in terms of u, the 36, when you divide both sides by 36, you're going to get nice cancellation. So what does this become when you multiply 4 times 3u squared? 36u squared, right? 9 times 4, 36, because you have to square the 3 as well as the u squared. 36u squared, also 36v squared equals 36. And not only, so divide by 36, not only is it a circle, it's the best circle ever, it's the unit circle, right? if you have a favorite circle. I mean, I suppose you don't have to. So that's really the boundary of S, right? So S is really, I mean, to be technically accurate, S is the unit disk, isn't it? So it's U squared plus V squared is less than or equal to 1, right? But you'll often hear me and other mathematicians slip and say, the unit circle is S. Really, it's the unit disk. It's the circle and its interior, right? Do we really need a picture there? Certainly we don't need one of R, right? We could draw it easily enough, but if you really want one of S, and really you should be able to show this work on a test it's a good idea to show it just for, if nothing else, partial credit, right? So it's almost easier to draw it freehand first and then, getting a little off track there, but good enough. We'll pretend like that's actually looks like a circle. And then, let's see. So, oh wait, this is UV, right? So this is in the UV plane, and in here is our S, right? So that's what I would call step 2. And then in step 3, you set up the integral, and you know what I do right away? I put in the Jacobian so I don't forget it. So 6, we could put in dv du for now. We're going to change it anyway. But I put in that Jacobian right away so I don't forget it. And then, you know, I think it's really, in this case, unless you're asked to do it, excuse me, habit, muscle memory, let's put in S in this form, right? And then, by the way, what's the integrand? Oh, it's y squared, which is really 4v squared. So that's kind of the raw setup. We need to simplify it. Does everybody see why I didn't specify limits of integration? Because we're integrating over a circle, we're going to do another transformation into polar coordinates, aren't we? Yeah. Now, you should be able to set this up using maybe a representative vertical rectangle. You know, on the test, I could definitely ask you to set up something like that, know how to do it, right? So you got to solve for v is analogous to y, u is analogous to x. So if you were going to set it up using vertical rectangles, you'd have to solve for v in terms of u, and you'd have a square root, which gives the top of the circle, and a square root, an opposite of a square root, which gives the bottom of the circle, because the equation of the circle is u squared plus v squared equals 1. So you solve that for v, you're going to get a plus root, a minus root, representing the top of the circle, plus root, negative root for the bottom of the circle, and those are your inner limits of integration, right? And you should be able to set that up, as you've seen me do in the past. But if you're asked to get the answer, then why even mess with setting that up, right? Let's just go right to setting up the polar integral. Okay, what are we going to bring to the outside? 24, and then, okay, polar coordinates. Now, we're going to change our differential to r dr d theta, right? And then what does, okay, remember v is analogous to y, so what does v squared become? What is y in polar? R sine theta, so you got to square that, right? And that's v squared. So that would be what? R squared sine squared theta, like that. And then make sure you have the extra r factor. So we're good there. And then limits of integration, okay, you have to think radially, so what does, can you see that? Does that show up? Yeah, oh yeah, that shows up. What does r range from? 0 to 1, and theta is going to go all the way around. And then let's simplify it at least. 0 to 2 pi, 0 to 1, r to the what? Third sine theta dr d theta. I don't know if you guys want me to evaluate this whole thing, but I will tell you this, you should split it up, right? Limits of integration are constant. You can separate the function of theta from the function of r in the integrand. So if you did split it up into a product of two single integrals, what would it look like? Integral 0 to 2 pi of sine, did I forget the square? Yeah, I did. Sine squared theta. And then integral from 0 to 1 of just r cubed. And this is d theta, by the way. Don't forget those. And then this is dr. Does that make sense? You want me to finish this? Okay. How do you reduce sine squared theta? So you're going to use a power reducing identity, which sine squared theta is equal to 1 cosine of 2 theta all over 2. What happened to the division by 2? I took it out front, right? Make life easy on yourself. Do little things like that. I could go ahead and integrate this right now. Really doesn't matter. That becomes 1/4 r to the 4th. Evaluate from 0 to 1. And I'm going to bring the denominator of 4 out here as well. Does that make sense? So this whole thing is just 1 now. Does that make sense? Okay. So, so what does this become out in front? 24 divided by 8? 3. And then let's integrate this with respect to theta. What do we get? Theta, okay, minus 1/2 sine of 2 theta. Check it. Take the derivative. You get cosine of 2 theta times 2. Gets rid of the 1/2, right? And then evaluated from 0 to 2 pi. And plug in the upper limit. What do we get? 3 times 2 pi. Oh, you end up taking the sine. So minus 1/2 sine of 4 pi. Sine of 4 pi is, though, what is that? 0. So I'm just going to put, you don't even need that in there. But and then minus, what happens when you plug in 0? 0. So we just get what? 6 pi?